In 9.3, we're going to work at solving quadratic equations by graphing. And that is our learning objective, to solve quadratic functions by graphing. Our key vocabulary is what is a quadratic equation, what is an x-intercept, what are roots, and what is called the zero of a function. So these are things we've all previously discussed. Solutions, x-intercepts, roots, and zeros are all the same thing. So when we're solving by graphing, we're looking for the x-intercepts. Those are the solutions. So let's take a look at what this will look like. If I want to go ahead and graph this function, the first thing I would want to do is I would want to locate the vertex. Okay, so I'm going to take, the x-coordinate of the vertex will be the opposite of b. Remember, we're working in ax squared plus bx plus c. So b is 5, so it's the opposite of b over 2 times a, and a in this case is 1. It's the coefficient there with x squared. So I'm going to have negative 5 halves. Okay, that's the x-coordinate of the vertex. So negative 5 halves is 1, 2, and a half. Right, so it'd be right about there. And I know that I have an axis of symmetry that goes through that, so I'm going to go ahead and put that in. So that will help me a little bit. And then I want to find the y-coordinate of the vertex. So the way I do that is I take the value of x and I plug it in. So I'll have negative 5 halves squared plus 5 times negative 5 halves plus 6. And what I'm going to want to do now is I'm going to want to have common denominators for everything, because I'm instantly going to have fractions here. When I square negative 5 halves, that's going to be 25 fourths. So it's negative 5 squared, which is 25, over 2 squared, which is 4. So I need fourths. So here I'm going to have negative 25 halves, but that's going to be negative 50 fourths. And then 6 is 24 fourths. Now we got something pretty workable. I've got common denominators. So I have 25 plus negative 50 is negative 25. Negative 25 plus 24 is negative 1 fourth. So my vertex is going to be right about here, negative 1 fourth. Okay, so my vertex is at negative 5 halves, negative 1 fourth. And now I want to look at finding the other values. So I'm going to pick 2 points to the right or to the left of the axis of symmetry. I'm going to use negative 2 and negative 1. I could use negative 3 and negative 4, and it wouldn't really make any difference at all. So I'm going to go ahead and create a t-table here. I'm going to choose negative 2 and negative 1. I normally pick the smallest numbers possible. That's typical for me. When I plug negative 2 up here, I'll have negative 2 squared, which is 4, plus 5 times negative 2, so that's minus 10, plus 6. And you'll notice I'll have 4 minus 10 is negative 6, plus 6 is 0. So that's a solution right there. That's a root, that's a 0, that's a solution, because I hit an x-intercept. When y is 0, and that's why they're called zeros, when we have an x-intercept, the y value is 0, so we call them zeros. Right? So I know then that if I was 1/2 to the right of the axis of symmetry at 0, I'll be 1/2 to the left. So my solutions are negative 3 and negative 2, which makes sense from what we've learned by factoring. If I factor this, I want factors of 6 that add up to be 5, that's 2 and 3. I'll have x plus 2 times x plus 3. And my solutions from this would be negative 2 and negative 3, so that's the same. I could continue on with graphing, but what's the point? I'm supposed to solve, and I've already found the solutions. So I know that my solutions are x is equal to negative 2 and negative 3. So once I find the x-intercepts, there's no point in my continuing. If I had, I would have had negative 1 squared is 1, plus 5 times negative 1 is minus 5, plus 6, and this is going to be 2. So here I would be at 2, and here I would be at 2. And this is what my graph would look like. It would go like that. But the key part I want is I want the x-intercepts, and I've already got them. Okay, so if we move along here with solving a quadratic equation having one solution, and remember, one solution is really one repeated solution. One repeated solution. I want to go ahead, if I'm just going to graph it, I'm still going to start with finding the x-coordinate of the vertex. It's the opposite of b, so that's the opposite of 8, over 2 times a, which is 1. Negative 8 divided by 2 is negative 4. So I know that the x-coordinate of my vertex is at negative 4, so that's 1, 2, 3, 4. That's where my axis of symmetry lies. And when I go ahead and I also know that my vertex is at negative 4 something. And when I plug that in to a t-table, I'm going to have negative 4 squared is 16, plus 8 times negative 4, that's going to be minus 32, plus 16, and you see that's 0. Well, that's complicated because when my vertex is at the solution, that's what happens when I have a repeated solution. So this is my vertex. It's only going to hit in one place, and that's kind of what happens. If I want to continue to graph it, I'd put in negative 3 and negative 2. Again, the smaller values as I move away from the axis of symmetry. And this will give me 9 minus 24 plus 16. And that's going to be 1. And when I plug in negative 2, I'll have 4 minus 32. Excuse me, I'll have 4 minus 16 plus 16, and that's going to be 4. So these points would look like this, 1, 2, 3, 4. And these points would look like that, and this is what it would look like if I graphed it. So you can see that when we have a repeated solution, what's happening is the vertex is on the x-axis, and that's what that looks like. Sometimes we have what they're going to say is no solution. The real truth is it's two imaginary solutions. And what that looks like is my quadratic function, when I graph it, is not going to hit the x-axis. So if I put this in the correct form, I'll have 3x squared minus 2x plus 1 equals 0. And I'm going to take the opposite of b over 2a for the x-coordinate of the vertex. So that's going to be the opposite of negative 2, which is positive 2, over 2 times 3, which is 6. The 2's are going to cancel. I'm going to get 1/3. Okay, so then I know I have a axis of symmetry at 1/3. That's not quite 1/3, but let's move it a little closer. About there. Okay, and then if I go ahead and do an input-output table, now I could pick 1 and 2, or I can pick 0 and 1 and negative 1. I actually prefer 0 and negative 1. I'm going to pick 0 anytime it's given as an option, because I know 0 minus 0 plus 1 is 1. So at 0, I'm at 1. That means, well, we're going to talk about that, the means in a second. So that was 1/3 to the left. That means 1/3 to the right, which would be at 2/3. I'll be at 1. And when I plug in negative 1, I'll have negative 1 squared is 1 times 3 is 3, minus 2 times negative 1, so minus negative 2 is 5, plus 1 is 6. So we'll go over here to 6. 1, 2, 3, 4, 5, 6. And that means, so that's 1 and 1/3 away from the axis of symmetry, so that's going to be here at 1 and 2/3. Okay, and we still haven't found the other coordinate of the vertex. I know my vertex is at 1/3, but I haven't plugged that in yet. Excuse me. And when I plug 1/3 in, I'm going to have 3 times 1/3 squared. So I'm going to have 3 times 1/9, right? Which is going to simplify to be 1/3. And I'm going to be minus 2 times 1/3. So that's going to be minus 2/3. And it's going to be plus 1, which is 3/3. So I have 1/3 minus 2/3. That's a negative 1/3. Plus 3/3, that's going to be 2/3. So this is where I am. And you see, what happens with my graph is it never actually hits the x-axis. So they say I have no solution. The reality is my solutions are imaginary numbers. And right now we're just staying in the realm of real numbers. This is what it looks like. Two solutions, one repeated solution, two imaginary solutions. This is what it looks like when you've graphed them. Intersecting the x-axis in 2 points, two solutions. A repeated solution has the vertex on the x-axis. And two imaginary solutions, or no real solutions, doesn't hit the x-axis at all. Okay, if we want to find the zeros of a quadratic function, again, I'm going to do the opposite of b. So it's going to be the x-coordinate of the vertex will be the opposite of 1, negative 1, which is 1, over 2 times 1. So it's going to be 1/2. Again, I'm going to go ahead and drop in a axis of symmetry at 1/2, and I'm going to find that. And I'm also going to do 0 and negative 1 again, because I love 0 as a number. So when I plug in 1/2 with this particular problem, I'm going to get 1/4, because that's 1/2 squared. I'm sorry, 1/4 minus 1/2 minus 12. So that's going to be a big negative number. Right? So 1/2 minus, or sorry, 1/4 minus 1/2 is negative 1/4. Minus 12 is minus 12 and 1/4. That's where my vertex lies. That's way down here. 12 1/4. When I plug in 0, I'll get negative 12. That's going to be about here, and then consequently we'd also have a point here. And when I plug in negative 1, I'm going to have negative 1 squared is 1 minus negative 1, that's plus 1, minus 12, that's negative 10, which is right here, and consequently there. So when we look at this, that's not, I haven't found any solutions. What I found right now is I found this part of the graph, and it's not really helping me. I'm going to have to go a little further. If we think about what happens when we're working with solving by factoring, I could look at factors of 12 that have a difference of 1. That would be 4 and 3. So I know I'm going to have x minus 4 times x plus 3. So when I look at these, this is taking an equation from standard form and putting it into what we call intercept form, because these are the solutions. I know I've got a solution at 4, 1, 2, 3, 4, and one at negative 3, 1, 2, 3, right there. And this is how my graph will finish. Equally, I could just have continued to try numbers until I found a 0. I have negative 3 squared is 9. Minus negative 3, that's plus 3 minus 12, and that gives us 0. And we'll get the same when we plug in 4. But solving by graphing is not one of the best ways to solve. So you can also use factoring to help you get to the solution a little quicker. I could have continued trying numbers. When I went out, I could have tried negative 2, then negative 3, and I would have found that I kept getting closer and closer to the x-axis, and I would have eventually found it. Instead, I went ahead and shortcut it. Sometimes what you get is not going to be, we're not going to end up being in a simple solution that has whole number answers like we had in the last problem. And this is an input-output table from a function, and we're changing the values of x by tenths, right? I would never probably want to do that. It's a lot of work. And there are other ways to go about solving this function, like throwing it into a graphing tool and finding the x-axes. But if I'm working with a table like this, I can tell that the 0, it lies between here. Here I know that the output is positive, so it's above the x-axis, and here it's below the x-axis. So somewhere between negative 3.8 and negative 3.7, there was a solution. But because they wanted the nearest tenth, I see that this value is closer to 0 than this value, so we're selecting negative 3.7. And when we look for the other solution, you can see we're above 0, then we go below 0 for a goodly period of time, and then we go back to above 0. And you'll see, of course, that these values are the same because we're working around, You see that these values are the same because we're working around the axis of symmetry, and when we're the same distance from the axis of symmetry, our outputs are going to be the same. So it's natural that that's what happened here. And you can see then that, again, the negative 0.3 is closer to 0 than negative 0.2 is for the outputs. Right? So this would be working with a table to try to approximate, because we're only going to the nearest tenth, what the solution is. And if we wanted to work on a problem that was a little more into the real world, we're looking at a track and field athlete who's throwing a shot put, and it has initial vertical velocity of 40 feet per second. So we're going to go ahead and write, again, we're going to use that height is equal to negative 16t squared plus the initial velocity times time plus the initial height. Okay, and when we look at this problem, we've got initial velocity. I know that my height will be negative 16t squared plus, right, an initial velocity of 40 feet per second times time plus the initial height, and you can see she releases this at 6.5 feet. And if we want to use the equation to find the time that the shot put has been in the air, then I know that when it lands, the height is 0. So this is the time it takes to land to the ground. So I have negative 16t squared plus 40t plus 6.5. And there are a lot of different ways I could go about this. I haven't done this yet, so what I'm going to do is I'm going to show you what it would look like if I solved this with Desmos. So I'm going to do the Desmos graphing calculator, and I'm going to graph this. So I have negative 16, I'm going to say x squared plus 40x plus 6.5. And this is what I'm looking for here. I have negative 0.153 and I have 2.653. Now, which solution is it that I want? Well, remember, when we think about how our shot put is traveling, it's starting here. So when you think about the x-axis being time, if it's starting here at time 0, this negative value, that happened in the past. That's obviously not the one we want. What we want is 2.653 seconds. That's what we want. So what we're going to get is that our time is equal to 2.653. When we think about what happened with that negative value, that would be if the shot put was here and I launched it upward with the same velocity of 40 feet per second, that time is the time in the past that I would have had to launch it so that it can get up to the 6.5 feet that it is in the initial part of the problem. So when you're working with these types of problems and you get two solutions, you know you're looking for the positive solution because the negative time is in the past. So just to give a quick wrap up, remember we're looking at solutions of an equation. We can find them by factoring, we can also find them by graphing, and there are always the x-intercepts. Okay, and also the zeros because they are the values of x that have an output of 0, and we also call them roots. Okay, so those are important things to remember.